my name is Wen-fai Fong, and good morning, everyone. So my goal today is to hopefully get you excited about short gamma ray bursts, whether it be about the great strides that we've made over the past decade or about the open questions that remain to be answered. This is an artist rendition of a short gamma ray burst, not a real picture, although I wish. Okay, so why study short gamma ray bursts? Well, the most likely progenitors of short gamma ray bursts are compact object mergers. These are two neutron stars, potentially two black holes maybe, or a neutron star and a black hole gravitationally bound in a binary system. They eventually merge and explode. And so we think those compact object mergers also produce gravitational waves. We actually know that now. And they also may be likely sites of heavy elements, in particular R process elements. The very heaviest elements. This is a picture of gold just because this is interesting to average normal people, but not that astronomers aren't normal, but just to give you the idea. All right, so Rem gave a great overview of kind of the details of the explosion. This is the very highly simplified basic picture of what's happening inside a gamma ray burst. So we have some sort of progenitor. It gives rise to a central engine. This is transient accretion onto a black hole via a hypermassive neutron star that may or may not survive for a long time. This gives rise to a relativistic blast wave that gets shock heated and produces prompt gamma ray emission. And the remaining portion of the outflow goes on to interact with the circumburst medium and produce a synchrotron emission, in principle detectable in X-ray through radio wavelengths. So every gamma ray burst has these two components, this prompt short gamma ray emission, and then this long-lived, long wavelength afterglow. And I just have the toy electromagnetic spectrum down here just to show you that gamma ray bursts, even though they're called gamma ray bursts, are really visible over 9 orders of magnitude in frequency. Okay. All right, so just focusing on the prompt emission, Rem also showed this plot, but you can see that the duration distribution is bimodal, and with a separation at about 2 seconds. So everything greater than 2 seconds is generally considered a long gamma ray burst. Everything less than 2 seconds considered a short. And so over the past couple of decades, it's been shown also that these probably map to two different progenitors. So long gamma ray bursts are likely, we know that they're from the collapse of very massive stars, and we know this because of their association with type 1c supernovae. So every time we see a long gamma ray burst that's low redshift enough to be able to detect a supernova, except in 2 cases, we've actually been able to detect a type 1c supernova. So the supernova has acted as a smoking gun, linking long gamma ray bursts to their progenitors, while short gamma ray bursts, despite deep optical searches and in the near infrared, following the gamma ray burst, we've never been able to detect a supernova following a short gamma ray burst. So this means that there must be some other progenitor system responsible for short gamma ray bursts. And so I'll try to convince you today that we think the most likely progenitor are compact object mergers. Okay, so that was a prompt emission, now just focusing on the afterglows. So long gamma ray burst afterglows were detected in 1997, but the discovery of short gamma ray burst afterglows was delayed by 8 years. They weren't detected until 2005. And the main reason is because short gamma ray burst afterglows are very faint. And so it took the community a while to actually figure out that we actually really need the most sensitive instruments in the game of detecting short gamma ray burst afterglows. So the first X-ray afterglow was detected by Swift. This was in 2005, and this is the X-ray afterglow position superimposed on an optical image, and you can see this provides a localization uncertainty of a few arc seconds. And so it's probably in association with this galaxy just by probability, given the brightness and distance between the afterglow and the host, but it's impossible to say exactly where it occurred within its host galaxy. And so we really want sub-arc second localization via the detection of either an optical or a radio afterglow. So these were the first optical and radio afterglow detections for short gamma ray bursts. This is, again, the X-ray position, and then the optical afterglow is right there. So with an optical position, you really can get to sub-arc second precision and not only know that was definitely the host galaxy, but also sub-arc second localization within the host. And again, the same is the case for the radio afterglows. Okay, so afterglows, and especially in short gamma ray bursts, are key to localization and placement within a host galaxy. In fact, because short gamma ray burst afterglows are so faint, it's impossible to get nearly impossible to get a redshift from the afterglow itself. And so we rely on an association to a host galaxy to actually get the distance to the burst. Okay, it's also important to note that only 10% of SWIFT gamma ray bursts are actually short. So SWIFT is the main satellite or workhorse that actually localizes and detects gamma ray bursts, but only 10% of them are actually short. And so because of the relatively low detection rate as well as the relative faintness of their afterglows, there's been a global effort to actually chase these afterglows, in particular for the short gamma ray burst game, at all wavelengths. So we're still in the regime where every short gamma ray burst is chased after by telescopes around the world. These are just some programs that I'm actually involved in, but there's many PIs in this room who actually lead programs around the world. And so it's also important to get afterglow information at a broad range of wavelengths, and I'll show you why that's important later on. Okay, so back to the basic picture, the main things I want to focus on today are the progenitor system and show you why we think they're compact object mergers. I also want to focus on the collimation, how tightly collimated we think these short gamma ray bursts are, and then finally focus on the afterglow, which can give us insight into the physical properties of the burst. Okay, so that's the outline. Progenitors, collimation, afterglow properties, and then finally I'll say a few words about the connection to gravitational waves and what we can learn about from short gamma ray bursts. Okay, so in the progenitors, I'll focus on the host galaxy environments as well as potentially a smoking gun licking short gamma ray burst to their progenitors. So long gamma ray bursts are, I think I remember what I wrote. Long gamma ray bursts are exclusively found in star-forming galaxies. And so throughout this talk, I'll be using long gamma ray bursts as a foil for short gamma ray bursts because we know so much more about them. So this is a placemat of long gamma ray burst host galaxies. Short gamma ray bursts, on the other hand, come in all types of galaxies, and these are just two examples. And using optical spectroscopy, we can actually type them as either star-forming, based on their strong emission lines, or elliptical, based on their deep absorption lines. So these are two examples of short gamma ray burst host galaxy spectra. And just taking a compilation of about 35 of these, we found that about 70% are star-forming and 30% are elliptical galaxies. So the sizable fraction of ellipticals is commensurate with an older stellar progenitor. Furthermore, the star-forming galaxies of short gamma ray bursts are not extremely star-forming. They have the typical properties of Milky Way type galaxies. So in contrast, long gamma ray bursts are very star-forming, highly star-forming, and are generally lower mass galaxies. But the star-forming galaxies of short gamma ray bursts generally have properties in line with the Milky Way. And in particular, their ages, they come from a broad range of stellar population ages, and this, in the context of the compact object merger progenitor, may map to a range of merger timescales. Okay, commensurate with an older stellar progenitor, and using the relative rates of short gamma ray bursts in star-forming and elliptical galaxies and comparing to predictions, we can tease out a delay time distribution with a power law decline of about tau to the minus 1. So this is not unlike the delay time distribution for type 1a supernovae. Okay, another diagnostic is looking at the locations of the short gamma ray bursts within their host galaxies. And to use this, to analyze this, we use Hubble Space Telescope observations. And the reason that this is such an important diagnostic is the combination of the delay times or the merger timescales as well as neutron star black hole kicks means that by the time we see the short gamma ray bursts merge and explode, they should have moderate offsets from their host galaxies because they have the ability to migrate with a certain speed over a certain amount of time. And so for each gamma ray burst, we measure what's called the offset, the projected offset on the sky between the afterglow location and the host galaxy center. So putting it all together, this is the projected physical offset distribution for short gamma ray bursts and also long gamma ray bursts. So this long gamma ray burst distribution is actually Peter Blanchard's work updated as of this year, and he analyzed over 100 long gamma ray bursts, so this is a relatively robust result. And you can see long gamma ray bursts sit at about 1 kiloparsec from their host galaxies, while short gamma ray bursts are much more offset from their hosts at about 5 kiloparsecs. And then these gray lines are predicted distributions from population synthesis of neutron star binary mergers. And you can see that the short gamma ray burst distribution lines up relatively well with those predictions for compact object mergers. Furthermore, normalizing the offsets by the size of the host galaxies, we find that only 1/5 of short gamma ray bursts lie within 1 half-light radius, and also that 20% occur basically in the middle of nowhere at greater than 5 half-light radii away from their hosts. So we find that spatial locations are actually indicative of kicks, and the inferred kick velocity, taking into account the stellar population age as a proxy for merger timescales, indicates a kick velocity of 100 kilometers per second or so, about a median. Okay, and then another way to look at the locations is actually to analyze the host galaxy light distribution and where the short gamma ray burst falls with respect to that. So I'll just build up this plot as it's a little confusing if you've seen it for the first time. This is a cumulative distribution of the fractional brightness level, and this line corresponds to a 1-to-1 distribution, a population that perfectly tracks its host galaxy light. And these are where things would fall. If something's correlated with fainter regions, it would not be on this side of the diagram. If correlated with brighter regions, it'd be on this side of the diagram. So long gamma ray bursts and core collapse supernovae, we know they come from massive stars, and they're pushed really to the brightest regions of their host galaxies. This is, again, Peter's work from this year. And so you can see that they're really pushed to kind of the brighter regions of their hosts. This is commensurate with their massive star origin. Short gamma ray bursts in the rest frame UV, which traces star formation, you can see that they really overall do not track their host galaxy light. They're weakly correlated with their host galaxy light, and 55% of them really occur in the middle of nowhere in terms of star forming regions. And the same is true in the rest frame optical. This traces stellar mass. You can see again overall, they really don't trace the stellar mass distribution of their hosts. And so this combined with the spatial offsets, probably the strongest circumstantial evidence we have that short gamma ray bursts do in fact come from compact object merger progenitors, that they had to form somewhere and then migrate and then explode. Okay, but of course it would be really great to actually have a smoking gun linking short gamma ray bursts to their progenitors. Just like type 1c supernovae serve that purpose for long gamma ray bursts, it'd be nice to have that for short gamma ray bursts. So if we believe that compact object mergers produce short gamma ray bursts, then one main model that's been presented is the production of an isotropic transient from the radioactive decay of heavy elements created in the merger. And this is our process, kilonova or macronova, and it's about 1,000 times brighter than a nova. And so the neutron star actually ejects neutron-rich material, and the radioactive decay of which will produce a transient. And this transient in recent times has been expected to peak in the near infrared on about 1 week timescales. So they're distinct in both their timescales and their colors from a typical GRB afterglow. Okay, so in 2013, we think we were successful in actually finding the first kilonova following a short gamma ray burst. So this was 130603b. And Hubble Space Telescope observations were taken after this burst was localized via its optical afterglow. So observations were taken in the optical and near infrared at 9 days, 30 days, and then a subtraction reveals a source in the near infrared that's not present in the optical on long time scales. And this is the same plot, same as this image, but just in light curve form, absolute magnitude, this is versus time. And you can just trust me that this is about 9 days, and there's this near-infrared excess that's not present in the optical. And so comparing this to kilonova models, we can actually, for the first time, get the properties of dynamical ejecta of neutron star mergers. In particular, their ejecta velocity and also their ejecta mass. And so this is really the first potential direct evidence for a compact object merger origin, and really kind of serves as a smoking gun linking short gamma ray bursts to their progenitors. Okay, so moving on to collimation and how it affects the energy scale and event rate. And so this work has kind of focuses on whether short gamma ray bursts are highly collimated or spherical. So if they look like this affectionate beluga whale or an exploding apple, or somewhere in between. So the way that we measure this is from the jet break, as Rem went over. This is just a toy light curve of a gamma ray burst. And so by tracking the temporal evolution of the short gamma ray burst over time, we can actually hope to find this break that maps to the opening angle of the jet. And so in general, a later break corresponds to a wider opening angle, although this assumes on-axis orientation, and Andrew, I'm citing you here. And so this assumes on-axis orientation, as Hendrick and Andrew's work have suggested that if you're off-axis, that could disguise a jet break. Okay, so this is the overall distribution for short and long gamma ray bursts, and this was updated as of last week. There was a new short gamma ray burst with a 5-degree jet that was published. So this is long gamma ray bursts in red and short gamma ray bursts in blue. And you can see we have now 5 opening angle detections. And the paucity of detections is really due to the fact that mainly due to the fact that short gamma ray burst afterglows are faint. So you already start at a very low flux level, and it's generally more difficult to actually catch the jet break before it fades away. Okay, so assuming a 30-degree maximum jet opening angle, and this is just theoretically motivated because simulations of post-merger accretion suggest that there might be something like a 30 or 40-degree maximum on the opening angle. This leads to a median opening angle of 16 plus or minus 10 degrees. So we're still really in the regime where every opening angle really counts in determining the median opening angle. Okay, so why do we care about the collimation? Well, this has major implications on both the event rate and also the energy scale. So just as an exercise, if the jet opening angle is about 10 degrees, then in terms of the energy scale, that means the true energy scale is 100 times less than the isotropic equivalent energy scale. Because if we're just collimating the energy into a narrow jet, that means that the true energy is much lower. In terms of event rate, the converse is true. This means that the true energy scale is actually about 100 times greater than the observed energy, the true event rate is 100 times larger than the observed rate. That's because we only see if they're highly collimated, we'll only see the jets that are actually pointed at us, and there'll be many events that are occurring that we'll never see. And so the true event rate will be something like 1,000 per gigaparsec cubed per year, and then just in parentheses, I show the event rate within a advanced LIGO volume of 200 megaparsecs. So you can see we would expect about 30 per year if this is true. And this matches well to predictions of neutron star binaries, the prediction of neutron star binary rates, also from the extrapolations on the galactic rate, as well as from simulations. Okay, afterglow properties. So I just want to give you a census of short gamma ray burst afterglows and how we can use the short gamma ray burst afterglows to map to their explosion properties, and then spend a few minutes talking about kind of atypical behavior that we've seen in short gamma ray burst afterglows. Okay, so as Rem also showed, we think that afterglow emission is synchrotron has a very characteristic spectrum. There's these 4 power laws with these 3 break frequencies, and the reason that we want to actually look at short gamma ray burst afterglows in all wavelengths is because by mapping them in the radio, optical, near-infrared, and X-ray, we can actually get a sense of what this entire spectrum looks like. And the good thing about synchrotron is it actually maps to basic explosion properties of the burst, in particular the kinetic energy and the circumburst density. So by collecting as much information as we can and all these different wavelengths, we can hope to tease out these basic explosion properties. So early studies focused on the afterglows suggested that maybe they have relatively low circumburst densities and low energies compared to long gamma ray bursts. So this is the first afterglow for which we were able to detect it in the radio, optical, near-infrared, and X-rays, and you can see fitting a synchrotron model gives relatively low densities and low energies compared to long gamma ray bursts. Furthermore, Alicia Soderberg collected all of the short and long gamma ray bursts for which there were density measurements at the time, and you can see short gamma ray bursts in black compared to long gamma ray bursts in gray have generally lowered circumburst densities than long gamma ray bursts. And so the early afterglow studies in 2005 and 2006 pointed to generally low densities of about 10 to the minus 3 to 0.1 particle per centimeter cubed. Okay, so now what is the status as of 2016? Well, as far as the number bursts detected over the number observed in that waveband, 75% of X-ray afterglows are detected, 35% are detected in the optical or near-infrared, and only 7% in the radio. And so one of the key questions is actually, what do the lack of afterglow detections tell us about their basic explosion properties? Okay, so this is putting an entire sample of the past decade of short gamma ray burst afterglows. This is the resulting distribution in circumburst density, and then the median for long gamma ray bursts of about 1 particle per centimeter cubed. So you can see that the circumburst densities of short gamma ray bursts are relatively low, 4 times 10 to the minus 3 particle per centimeter cubed, that 95% of events occur at densities lower than 1 particle per centimeter cubed. So these are extremely low circumburst densities and commensurate with the fact that we think that these progenitor systems are kicked. And we also get the kinetic energy, and this is a kinetic energy distribution, isotropic equivalent, and we find again that they're about 2 orders of magnitude lower than those for long gamma ray bursts. Okay, because I'm running out of time, I'll skip over this atypical behavior section, but you can ask me about it in the questions if you want. So I just want to talk a little bit about the connection to gravitational waves and what we can actually learn from the population of short gamma ray bursts, in particular about the detectability of off-axis afterglows and kilonovae. Okay, so compact object mergers we think produce short gamma ray bursts, kilonovae, and also gravitational waves. And gravitational waves, in the era of gravitational waves, will only provide positions of tens to hundreds of degrees, square degrees. And so it's really important to figure out what is the best electromagnetic counterpart to actually localize these gravitational wave signals very well. Okay, so in terms of off-axis afterglows, currently gamma ray bursts are detected more or less on axis, but the gravitational wave emission is relatively isotropic, and so it doesn't really care what direction the gamma rays are pointed in. And so the most gravitational wave events actually will be detected off-axis. And so we can actually use what we know about on-axis short gamma ray bursts to tell us what off-axis gamma ray bursts will look like, off-axis afterglows will look like. So using typical inputs from short gamma ray bursts and also within the 200 megaparsec volume of advanced LIGO, what do the off-axis afterglows look like? So I've done this for just the optical and radio so far, but these are the off-axis afterglow light curves for the optical at 200 megaparsecs, and just to show you a burst at about z of a half, and then also in the radio. And this is just using typical parameters, and also depends on the jet opening angle and also how far off axis you are. Okay, and these are just mapped to typical detection limits for various telescopes. And so an 8-meter class telescope would only get you part of the light curve. You would really rely on kind of an ELT to get a very good sense of the off-axis afterglow light curve. Whereas in the radio, typically 30 minutes on the VLA could really get you a great temporal evolution of the off-axis radio afterglow. And so off-axis radio afterglows may be promising sources, electromagnetic counterparts to advanced LIGO sources. Okay, and finally, as far as the detectability of kilonovae, these are optical and near-infrared, rest frame optical and rest frame near-infrared light curves models from Barnes and Case in 2013, where the gray shaded region maps to the most pessimistic and most optimistic model in their paper. And this just represents the range of models determined in their paper, and the luminosity generally depends on the ejecta mass and the ejecta velocity. And then Masaomi Tanaka also had models splitting into neutron star black holes and also neutron star. And also I want to point out that the kilonovae are very red, so you can see that the near-infrared luminosity is greater than the optical luminosity in general. Okay, and finally, Dan Kaysen also came out with a paper last year that modeled accretion disk winds surrounding a hypermassive neutron star remnant that can actually inhibit the production of very heavy elements, and so lower the opacities. And so this actually makes for an optically bright transient as opposed to, and less contribution in the near-infrared. Okay, so from short gamma ray bursts, we've been able to actually place limits, generally from when we actually pointed our telescope at us after a short gamma ray burst and there was nothing there, or after the optical afterglow had faded. And so this is what short gamma ray bursts can tell us. So for GRB 130603b, this is where it lies. Maybe according to these models, it might be from a neutron star black hole, given its large luminosity. So for short gamma ray bursts, this is what we can say. And so each of these limits represents a time when we pointed at the position of a short gamma ray burst and we didn't see anything, or after the afterglow had faded. So you can say it's challenging to actually detect kilonovae following short gamma ray bursts, and they're really not very sensitive to even the most optimistic kilonova models. However, at about 200 megaparsecs, of course, the objects are much closer, and so it's a little bit more promising to actually detect them. Unless they're even redder. So there was a paper from Los Alamos last year that suggested that the opacities are even higher than we thought, and that maybe these will be actually very pushed even farther into the infrared. Okay, so I'll just end with my summary because I'm over time. Thanks.
Your averaging of the opening angles seems a bit, at least to me, a little odd. Did you take into account that when you see it's a little complicated problem, but that when you see a small opening angle, its weight is larger than the one which has a higher opening angle?
Yes. You mean, let's see. Yes, I did take that into account. So for each event, I assumed a certain probability based on how well we know the opening angle, and also for the lower limits too.
Okay, a short question was, with the whatever n months of LIGO 01, what is some 90% confidence upper limit on the neutron star coalescence at this point in gigaparsec cube per year?
Oh, in 01? What is the rate, you mean? Yeah, we don't see any, yeah.
So I want a limit from that.
You made an estimate of the environmental densities.
Yeah.
On the order of 10 to the minus 3, and you gave us this nice curve. Have you gotten estimates for the similar estimates for binary neutron stars in our galaxy?
No.
To get a sense of that, because they would have experienced the same sorts of kicks that would bring them out, at least in your conceptualization, to regions of low density.
Yeah, that's a
It'd
good...
be nice to compare the two.
Yeah, that's a good question. I actually don't know. I mean, I think most of the... Yeah, I don't know how you would probe the densities without having an explosion there.
I didn't have an answer for that question.
Yeah, so I don't know.
Hi, correct me if I'm wrong, but I think you mentioned that black hole binaries might be progenitors for gamma ray bursts, right?
Yeah, there was...
Do you have it's not clear to me how that can be possible, but do you have any potential mechanism how that can be true?
There's some people in this room who have published papers on that. So that was just motivated by the fact that we saw a potential short gamma ray burst in conjunction with a binary black hole from advanced LIGO. I don't want to say my favorite model, though, off the record. But it's definitely an interesting question.
My question is on the same line. If two black hole merge and forms a gamma ray burst, do you expect a kilonova associated with that one?
I haven't seen any models that would actually produce a kilonova, mainly because you need a lot of mass ejected from a relatively, 0.1 to 0.3 solar masses or so in order to do that. And we don't necessarily expect that around binary black holes.
Okay.
Yeah. But Avi might have a remark. That's good. Oh, okay.
So there was a conflicting message between the first talk we heard and yours, in the sense that Rem mentioned that the probability distribution of burst durations for long GRBs can extend into the short domain and gives the right flattening and so forth. At the same time, there is evidence that these short bursts are something different. So can you please clarify whether you are in disagreement or whether you have a resolution to this?
So I think there's definitely probably there's no magic number at 2 seconds that says that all of them should be, all of the bursts less than 2 seconds should be compact object mergers. However, when just looking at the host properties from bursts that have durations 0.01 seconds to 2 seconds, we don't see any differences from just looking at the upper end. So there may be some contamination within the short gamma ray burst population from massive star collapse, but we don't think that is significant. The contamination fraction is significant. Mm-hmm.